In this video, we're going to do a partial proof of Green's circulation theorem. So let's first review the statement of the theorem and recall that the curve, we have a curve that encloses a region on the plane. So the curve has to be a simple closed curve. That means it is not self-intersecting, oriented in the counterclockwise direction, and the region that's enclosed by the curve does not have any holes in it. Let's suppose that our vector field is also two-dimensional with two components, and both P and Q have continuous partial derivatives on the region. Then we can evaluate the circulation integral, which is flow over closed curve, by finding the double integral of the K component of the curl. So this represents circulation density within the region that's enclosed by our curve. So this theorem is saying that if we measure the circulation along the boundary of a region, that will be equal to measuring circulation density on the inside. Note also that the circulation line integral right here can also be written as p dx plus q dy, and in fact, this is how I'm going to use it in this proof. So we'll restate Green's theorem below in yellow, where the circulation integral p dx plus q dy, again, this measures flow along a closed curve, is equal to adding up the circulation density on the inside of the enclosed region. So for this proof, I'm going to show that Green's theorem holds for a rectangle first, right? So that is a closed curve, and we'll show just the part where p dx, the line integral p dx, will be equal to the double integral of the negative partial of p with respect to y over the inside region. And if you want to show the other part, q dy is equal to this piece over in the double integral, then you can follow a very similar structure. So let's get started with the left-hand side of the integral over a rectangle. So I'm going to sketch a rectangle where the bottom parts go from A to B, side pieces, bottom and top, go from A to B, side pieces go from C to D. And I'm going to orient it in the counterclockwise direction. So the integral, the line integral on the left side of Green's, the piece that we're working with, p of x, y, dx, measures the first component with respect to x, so over small infinitesimal changes in x. But if you notice for our curve, for the rectangle, along the vertical edges, there is no change in x, only change in y. So if we were to think of this integral as the integral, let's label our edges of the rectangle C1, C2, C3, and C4. So the integral over the entire rectangle will be p measured along C1, where y is fixed there at a value of c, plus the integral of p measured along C2, where x is fixed and there's no change in x at all. So we'll have x is fixed at b, and y changes, so I'll do that. dx, that's over c sub 2, plus the integral along C3, where x changes but y is fixed at d, and there is a change in x, plus the integral over the last piece, the curve C4, where x is fixed at a and y is changing, so I'll just write that at y and dx. But one thing we should note here, I keep stressing this, is that along C2 and C4, there is no change in x. So dx in C4 and dx in C2 are 0, which means that this integral and this integral have values of 0, and they will not be part of our sum. And so the left-hand side, the line integral, now has become the integral along C1 of P, where x is changing and y is fixed at C, dx, plus the integral along C3, the top, P, y is fixed at D. But notice that C1, if we integrate from left to right, C1, x varies from a to b. So that's the integral from a to b of x c dx. And C3, well, because the curve is oriented in the counterclockwise direction, C3, x varies from b to a in the opposite direction. So I'm going to write the limits of integration there from b to a, and we know here that x is fixed, y is fixed at d. And we can combine these two integrals by making the second one an integral from a to b and changing its sign. So this becomes the integral from a to b of p of xc dx, oh, I'll put dx at last, minus p of xd, and all of this is with respect to x. So that is the result of the line integral in greens on the left. Now we're going to focus on, so we've done this part, we have an expression for it. I'm going to leave it there, and now we're going to work on the left-hand side, which will be the double integral over the region of the partial derivative of p with respect to y. So we'll see what my strategy for this proof is: work on the right-hand side and get to the same expression. All right, so let's go ahead and work on the right-hand side, which is I'm just going to do it in a different color so that we can distinguish here. Let's see, we'll do it in yellow. So the right-hand side, RHS, is the negative double integral over the region, which is the region enclosed by a rectangle, of del P del Y dA. And of course, it's the same rectangle that we're looking at. So I'm just going to do a quick sketch of the rectangle here so I can refer to it as we do the double integral. And recall our rectangle is oriented in the counterclockwise direction, a very, very messy rectangle here, but there we go. And okay, so we want to do a double integral over this region. And so anytime we do a double integral, we've got to decide, are we going to do y simple or x simple, or are we going to use polar coordinates? And so I think I'm just going to do y simple here, where we're going to integrate from the lower segment to the top segment, which means that y, the bounds for y, will be from c to d, and we need to do that as x varies from a to b. And since I'm setting this up as a y simple region, my outer bounds will be the bounds for x from a to b, and my inner bounds will be the bounds for y from c to d. And here we have del p del y dy dx. That is the order of integration. And if we work on the inside integral, we'll keep the negative on the outside. The inside integral is the integral from c to d of del p del y dy. But notice what's happening here. This is taking the derivative of a component of the vector field, which is a scalar function, with respect to y, and then integrating with respect to y. So when we take the derivative of p and then integrate the derivative of p, we get p. So this results in p of xy, where y varies from c to d, which will be p of x comma d. Applying the fundamental theorem here, we'll plug in d first and then subtract what we get when we plug in c. All right, that is the result of our inside integral. If we do the outer now, remember that we have a negative on the outside, integral from a to b of the result of our inside integral, p of xd minus p of xc dx. But because of the negative on the outside, I'm going to rewrite this as the integral from a to b and change the order here so that we have p of xc minus p of xd dx. And you might notice that this integral is the same as the one we ended with when we worked on the left-hand side on the line integral. So when we move up a little bit, you can see that this was the result from the right-hand side of the integral, the line integral in greens. This is the result of the the right-hand side, which is the double integral, and they are equal, which means we have completed the proof of Green's theorem over a small rectangle. And now we just need to generalize this to regions that are not rectangular. So we have one last step to do. We've proven one part of Green's, and as I mentioned earlier, if you want to do the Q part, you can repeat a very similar argument, but integrate first with respect to x, then with respect to y. So you can follow the same structure. But we're going to generalize this, since we know that Green's holds for a small rectangle, an infinitesimally small rectangle, we need to generalize Green's so that for regions that are not necessarily rectangular. So suppose that we have, and this is the famous diagram of Green's theorem, we have a curve that's oriented in the counterclockwise direction, and we want to show that Green's theorem applies to a general curve with it that encloses a general region. It does not have to be rectangular. So, all right, well, we know that we can split up this region on the inside into tiny little rectangles. And we know that Green's hold for one of these tiny little rectangles. So I'm going to zoom in to these rectangles. So let's say that I zoom in to the part that looks like this. And each one of the rectangles, remember, is oriented in the counterclockwise direction. They're infinitesimal, oriented in the counterclockwise direction, and we know that Green's hold for these rectangles. We should also note, though, that the circulation in the boundary of these rectangles, that the boundaries that are close together, that are the boundaries that are shared. So this is a shared boundary between the rectangles. The circulation or the flow along those boundaries is 0. Because remember how we measure flow? We measure how much of the field flows in a specific direction, and we measure that against the tangent vector. So when you have a shared boundary, in one direction the tangent turns one way, in the opposite direction the tangent's it's negative. So flow will be 0 because the dot product will be the same. Well, one's positive, one's negative. So, all right, well, if along the shared boundary circulation is 0, then we can see that the circulation among these two rectangles that share the boundary is the same as the circulation along the outside. And then we know by Green's theorem that that will be equal to the curl on the inside of the region, the circulation density on the inside. And we do that for all of the little rectangles that we have. When we split this up into an infinite number of rectangles, we do it for every single little rectangle, and we end up with the circulation along the boundary of our curve. As the rectangles become infinitesimally small, we don't have to worry about the parts that aren't exactly rectangular, like this piece or this piece, because when we break that up into infinite number of pieces, they're all going to be infinitesimally small. So ultimately, we end up with the circulation on the outside being equal to the circulation density on the inside of the region, which is a generalization of Green's theorem over the small rectangle that we just proved. So that is the end of the proof of Green's theorem done this way.